Hello everyone, my name is Partho Das, Assistant Professor, Department of Electrical Engineering, JS College of Engineering, West Bengal, India. First of all, welcome to my class. So today's topic, as you can see in the screen, that is the armature reaction in a synchronous machine, or it is mainly in the synchronous generator section. That section we are discussing about. So for the last few days in the previous classes, we have discussed about the alternator construction, alternator, different types of rotor, stator, the thing we have. Then we have seen the what are the different types of excitation methods we have. So now it is very important to understand what is the armature reaction of an alternator, and what are the effects of this armature reaction. So in the previous machine classes, maybe in the electrical machine 1 syllabus, you have the DC machine. So in DC generator, you have seen that you have already known that what is armature reaction. That means the effect of armature flux on the main field flux, that is the armature reaction basically. But there is some difference between the DC generator armature reaction and the alternator armature reaction. Why is the difference over there? The reason behind is that the in DC machine, what we have a stator. Over the stator we have a field winding, and that is the stationary part of the machine, and in the rotor section we have armature winding, that is the rotating part of the machine. Now when some supply is given to the field winding, it is generating some flux. That flux is cutted by the armature conductor, and due to that, when some fluxes are also generated in the armature conductors, so that flux is opposing the main field flux. So that we know that armature reaction, and it has two effects, that is demagnetizing effect and cross magnetizing effect. But what is the difference between between this alternator and this DC generator? That the main difference is that in that DC machine, uh, over the stationary part we have the field winding, and over the rotating part we have the armature winding. But in case of alternator, we have seen that the case is reverse. On the stationary side, that is over the stator, we have the armature winding, and over the rotor, that is the rotating part of the machine, there we have the field poles. Okay, so already we have discussed those things in the constructional features. So as these things are different, so now we have to find out what is the different characteristics we have in case of when armature reaction happens um, in the what I can say, the in the alternator. So that thing, that is the motto for today's class. The what is the effect of armature reaction in case of this alternator or three-phase synchronous generator. Okay, so let us see what is written over here, then we are going for the detailing case. So when the current flows through the armature winding of an alternator, a flux is produced by the resulting mmf. This armature flux reacts with the main pole flux, causing the resultant flux to reduce either less than or more than the original value. So but it may happen that sometimes it is sometimes if the flux are has the same direction and same polarity, so then it will be additive. If it has a opposite polarity, then it will be a subtractive. So like that way it will be more than or less than of that main um, field flux. Okay, so now let us see what are the effects, and if when this armature flux is reacting with the main field flux, then we are going to see that if flux is changing, how much is the change. Okay, and then what should be the value, or what should be the equation, like those things we are going to see that what is the overall concept of this armature reaction. And when armature reaction happens in the machines, in the alternative machines, so then what are the results? So that study we have to do now. So let us do. So now let's see. So it is a diagram. So what is the diagram? For simplicity, we consider the three phase. Obviously it is a three phase machine, two pole alternator diagram. So it is a saline pole machine, as we can see. Okay, um, now see what is written over here. So in this particular machine, this is this three supply, but as there are, we know that in the previous classes we have discussed that what is concentrated winding, when what is distributed winding, when we have done the pitch factor, distribution factor. So those thing, winding factor, those components we have done. So there we have discussed about those things, that is what is concentrated winding, what is distributed winding. Okay. And uh, here we are depending upon those concepts, we can discuss about the armature reaction in three conditions. What is the condition? One is the unity power factor condition, what is the lagging power factor condition, and one is the leading power factor condition. So let us see what is written over here, and then how we are going to discuss those things. So the winding of each pole is assumed to be concentrated. Okay, but the effect of armature reaction will be same as if a distributed winding were also used. So we are considering over here that whatever three phase windings are there, those are concentrated one, but the effect of armature reaction will be same if there is a distributed winding is present. At that time also, what are the effect? A concentrated winding, at that time also the same effect will appear. Okay, so the armature reaction in synchronous machine affects the main field flux, and um, and it may vary with the different power factor also. So let us know that we have to know what are the different conditions we have, and how we can deal with those things. Okay, so what is written over here? Here armature reaction is discussed for following three conditions, mainly unity power factor, yes, zero power factor lagging, and zero power factor leading. So these are the three conditions. The power factor can be defined as a cosine angle between the armature phase current. See, it is very important line. What is armature power factor for this particular case? The power factor can be defined as the cosine of the cosine angle between the armature uh, phase current and the induced EMF in the armature. That means in armature, whatever EMF is induced and whatever current is flowing, that angle is the phase angle, and its cosine is the power factor, obviously. So let us start with the armature reaction in unity power factor. So let us check what is there. So for that, for finding out what is the current value, what is the flux value for unity power factor, for lagging power factor, the leading power factor, we have to first we have to assume something. So what are the assumptions? So let us see what are the assumption we have made over here. So follow my pointer over here. So these are the three phase and phase current we have assumed. So let us check what is written over here. The direction of rotation of the rotor is considered clockwise. By applying right hand rule, the direction of induced EMS in various conductors can be found. The direction of rotation of the conductors is taken anti-clockwise with respect to the rotor poles. Okay, suppose that the alternator is supplying current at unity power factor. The phase and current IA, IB and IC will be in phase with their respective generated EMF, that is the EA, EB and EC. So that we can see actually. So as it is a unity power factor, that means we can say that there is no phase difference between the generated EMF E and the phase current I. Okay, so that's why as we can see that, so in the first so follow my pointer, in that phase the EA and IE are in the same phase, this EB into IB are in the same phase, EC into IC are in the same phase. So those are in the same phase. So those things these are the phasor diagram actually. Okay, so now let us see. So these are the EMF and current. Now let us see what are the um, position of those fluxes, three phase fluxes that we have that we are discussing. So these are the fluxes that we have um, used. So that is the phi A, that is the phi B, and that is the phi C. Okay, so now we will see that this current and flux, what is the value if we are going to consider different phase angle, because this is instantaneous value should be taken for the understanding and the calculation purpose. So we are going to take 0 degree, 60 degree, 30 degree, 90 degree, like that way 120 degree. So different phase angle we can consider, and for each case we are going to find out that what is the current value, what is the flux value. Then we can, then after that we are able to understand that what are the effects, of different kind of power factor on the armature reaction. Okay, so now very carefully see, this is the section where you have to give your concentration, so that you can very easily understand, and once you can understand one condition, you can do the same thing for different phase angle. Okay, so let us concentrate into this matter. So at t is equal to 0, the instantaneous value of current and fluxes are given by the equation shown below. So what are the equations, and voltage and current equation are given. So it is given that Ia is equal to, that is a phase a phase current, that is Im, and phi a is equal to phi m. So those are all maximum value. Im is the maximum current and phi is the maximum flux. Okay, so we are considering this Ia and phi a, both are the reference, and with respect to that other two component value we can find out. So what is there, so this is Ib. Ib is definitely minus Ib cos 60 degree. Okay, so now if we put the cos 60 value over here, that is half, minus half Im, and there is a phi b, so that is also minus half pi b, that is actually phi m cos 60 degree. So like that way, for case of IC we can find out that minus 1 by 2 Im, and in case of phi c we can find out minus half phi m. Okay, these are the things. Now this is the resultant, now point 1 by 2, 1 by 2 um, Im, or 1 by 2 phi m means 0.5 Ia or phi m. So those components value we have placed over here. See, very carefully just see. So we have a three phase flux. What are the flux? Phi a, phi v, and phi c. Now in this particular diagram you just check where those three fluxes are. So as we can see, so this is the reference line. So this is the phi a, which is equal to the phi m magnetizing flux. Now with respect to that we have to find out this phi b and phi c. So as you can see, this side is the phi b and this side is the phi c, and each case it is half of phi m. So this is half of phi m and this is half of phi m. Okay, so now, so if we resolve those in horizontal axis, so resolving along horizontal direction we will get, so what we will going to get. Now we want to find out, this is the horizontal axis, so we over this horizontal axis we want to find out what is the total effect of the flux, three phase flux. So as you can see over here, phi a is on the axis of this horizontal line. So now we have to find out what is the effect of this phi b and phi c over this horizontal axis, correct? So as you can see, there is an angle of 60 degree. Yes, correct, as you can see. So that will be like this way. So this total horizontal component is equal to minus phi a minus phi b cos 60 degree. Yes, there is a cos. Okay, and minus phi c cos 60 degree. So these are on the second and third quadrant, that's why they are all minus we are using over here. So that is horizontal flux is equal to phi m minus that is already we have find it out, this phi b value. What is the phi b value? Here see, there is phi b is minus half phi m, minus half phi m that we have placed. Okay, and with that cos 60 degree is half, this is the 60 degrees over here, this one for b, this 60 degree, and for c this is the 60 degree. Again from the previous phi c value we have placed half phi m into half. So the total resultant that is coming, that is horizontal axis, that is minus 1.5 phi m. Now, like the same way, we can find out the vertical axis, the resolving the vertical axis, and we can find out the resultant flux. So now, if we do that, see, it is in the horizontal axis. So what are the effects of this one in this axis? That must be zero. That must be zero. So that's why, see, in this particular equation there is no flux of phi f flux is present, because if it is shifted 90 degrees, so there will be no flux, correct? So in this vertical axis there will be no effect of this one, so it has the effect of this flux and this flux only. So what is the angle between, see, from here, from this c axis to this vertical, what is the angle? If total is 90 and it is 60, so what is the rest? 30 degree. So like this, so if we extend this vertical axis here, and what is the angle between this B and this vertical axis? That will be again 30 degree. So we have to consider cos 30 degree angle. See, same way, minus or vertical axis resultant is given by minus phi b cos 30 degree plus phi c cos 30 degree. So now phi b, what is phi b? Minus half phi m, here also half phi m, so that putting those values, so it is total coming, that value is 0. So in the vertical axis it has a um, it has a zero flux, resultant flux is appearing. So what is the resultant armature flux is given by, that is the horizontal axis under root horizontal axis square flux square in plus the vertical axis flux square. So if we put that, so we can find out that is the 1.5 phi m. So this is the resultant flux when we are considering t is equal to 0. So that is the effect of armature reaction when t is equal to 0. So now if the rotor is now rotated 30 degree in the clockwise direction, the corresponding phasor is shown in the figure below. So now first one, it was ia was in this axis, I phi, ib and ic. So we have just rotated 30 degree, we have shifted somehow. So omega, now instant, this is omega t is equal 30 degree. Okay, so after knowing this, the omega is equal 30 degree, we have used those value over here. Okay, so what is the ia? So that is cos 30 root 3 by 2. So we have know now the value ia is root 3 by 2 im, and phi a is a root 3 by 2 phi m. So like this way, see, now this is the phi b, ib is on the axis of um, horizontal axis. So in the horizontal axis, this current and flux doesn't have any value, already we have seen in the previous cases. So here the for the ic, it is also must be minus root 3 by 2 phi m, and for case of phi c, that is minus root 3 by 2 phi m. Okay, so the resultant flux, we want to find out. Okay, again we are going to find out the vertical and horizontal, then there will be result in the same procedure. So that means, that's why I have told you that once one thing you can understand, then for each 30 degree or 60 degree rotation, we can find out the same thing, and we will check what is the value. So we can, after checking all things, we can find out that in each case we have the same values. Okay, so doesn't have to worry, we will able to understand that one. Mm, Now, so this is 30 degree we have shifted. So this is the phi a, phi b is 0, phi a value is there, and phi b value is there, and this is the resultant. Okay, so this is the resultant, so we can find out the resultant. So for finding out the geometrical method, we have used over here. So from there we have drawn a perpendicular over this do line, and such a it is drawn such a way that is dm is equal to mo. So yes, this is phi ar is equal to od is equal to 2mo. So like this way, we can find out phi AR, that is a 2 cos 2 OC cos 30 degree, that is 2 root 3 by 2 phi m, that into root 3 by 2, that is the 3 by 2 phi m, that is 1.5 phi m. So that is the result also. Okay, so now what is written over here? So hence it is observed that the resultant flux phi AR sets off by the current in the armature remains constant in magnitude to 1.55 m, and it rotates at synchronous speed. When the current is in the phase with the induced voltage, and armature reaction flux phi AR lags behind the main field by 90 degree. This is called the cross magnetizing flux. That means what? Once again I am going to tell you. So that means the resultant flux phi AR sets up by the currents in the armature remains constant in magnitude equal to, what is the magnitude value? 1.5 times, that is 1.55 m, and it rotates at synchronous speed. When the current is in phase with the induced voltage, the armature reaction flux phi AR lags behind by the main field flux. That is, the when this voltage and current are in the same phase, at that time that phi AR lags behind the, that is the armature flux, armature reaction flux is lags behind the main field flux, that is by an angle 90 degree. That is known as the cross magnetizing. So once one flux direction is this and one flux direction is this, so what is the angle between them? That is a 90 degrees. So that is known as the cross magnetizing flux. Okay, so we have done this in the zero power factor. Now if that is not zero, unity power factor. Now we are going to do armature reaction in lagging power factor. At the same time we are going to do in the leading power factor. So what is the lagging power factor armature reaction? Yes, so lagging power factor means that now in between the induced EMF and the armature current, phase current, there is an angle, because it is lagging or leading. In both cases there will be angle. So for those case, if we just check what are the values, then we can say that. So here also we are doing the same thing. At t is equal to 0, we have calculated the values. So at that time phi a and ia has a 0 value, ib and phi b, ic and phi c has some value. What are the values? Root 3 by 2 im and root 3 by 2 phi m. So those are the values. And if we draw the resultant over here, so this one, so what is phi a? Again it will come, again see, again it is coming that 1.55 m. So now similarly if we do the same thing in case of, see, this armature reaction at leading power factor, if we resolve the phasors, and from there if we find out the values, as we can see over here, so there we can see that. So if we do the same thing, repetition, so what are the values? Same. So my point is, so um, my point is that due to the armature reaction and main field flux reaction, so always the flux is remaining constant in the machine, that is 1.5 times of the maximum flux. Okay, and when the direction of this armature reaction flux and the main field flux is um, are same, that time it is known as the magnetizing flux. That means it is additive at that time. And sometimes in the previous case we have that it has a 90 degree shipment in between them, so that time there is a cross magnetizing flux. And when both are magnetizing each other, that is the flux, armature flux and the main field flux, when additive, that is the magnetizing flux. So this is all about the armature reaction happens in the alternator. So I think it is clear to you. So what is we have done today? So we have done that. We have done that. What is armature reaction? How they affect at different power factor, leading, lagging, and unity power factor. So, and what is the current value? What is the flux value? What is cross magnetizing effect? What is the magnetizing effect? So those things we have discussed today. Okay. So that is all for today. Thank you.